Okay, lecture 20, and this is our last lecture of chapter 3, which is continuous random variables. So just to decide, we're going to look at how we would simulate data, specifically simulate a random variable. Next time, next lecture, we're going to be doing a case study where we're going to look at social distancing and simulating outbreaks and see what effects social distancing has. But first, let's get to lecture 20. So, simple question, you might not have thought about this. Like, so far, whenever we wanted to get, observations of a normal or a binomial, we go into R and we just do R binomial, R norm, and outspit some, random variables. How does it do it? Well, there's lots of different ways of doing that. I'm just going to introduce one, which is called the inverse transform method. And what it does is, most computers can get random numbers between 0 and 1. They can basically simulate from a uniform 0, 1. They don't actually get proper random numbers, they get pseudo-random numbers, and you can go and look at that on Wiki. Once you've got, what we're going to do is we're going to take those numbers, apply a transformation, and that transformation will then give us the distribution that we want. And this method is called the inverse transform method. I've seen it called the integral transform or the InverseCDF method. There's lots of different ways, but let's give the general version of the inverse transform method. So we've got a random variable x, and that comes from a distribution, and we know it's CDF, which should denote by capital F x of x. So how do I get this simulation of x? Well, first of all, what you do is you simulate an observation u from a uniform distribution. So that's going to be a number that's randomly between 0 and 1. The next thing we do is we take our CDF and we calculate its inverse, which I denote of capital F to the minus 1 of x. Then all we do is we apply that inverse CDF to u. And those numbers will spit out observations from our distribution that x has. So let's see an example. Let's say I want to do an exponential distribution of a parameter lambda. So 1, as we said, we will simulate u from a uniform distribution. 2, we will find the inverse CDF of that. Now I've written it there, f to the minus 1x equals minus log 1 minus x over lambda. We'll get to how I got that in a second. And then once we've set that, then all we do to get our x is we take our u, we go 1 minus u, we take the log, we divide it by our lambda, and we take the negative of that, and that number will be a simulated data point from an exponential distribution with a rate of lambda. So let's just quickly work out how we got our inverse CDF. So we know that our PDF, f of x, equals lambda e to the minus lambda x, for x greater than or equal to 0, and obviously we've got lambda greater than 0, for this to be a valid probability math function. If you go back to the lectures, you'll see that the CDF is 1 minus e to the minus lambda x. And again, that is for x greater than or equal to 0, lambda greater than 0. So let's get the inverse. So let's set y equal to this. Y equals 1 minus e to the minus lambda x. So that implies that we have e to the minus lambda x equals 1 minus y. Take the log of both sides to get minus lambda x equals the log of 1 minus y. So x equals minus the log of 1 minus y over lambda. So this is our f minus 1 x of x. So then I can use that to simulate. So let's see an example. What I'm going to do is I'm going to do an exponential with rate of 2. So here's the R code. What we've done is we've created some uniform. So in this case, I've created 10,000 observations from a uniform 0, 1 distribution. Then to get my x, all I do is I calculate 1 minus that. Obviously, it's doing element-wise vectorization. Take the log minus over 2. So is this looking right? Well, What I've done here is I've simulated that, taken the data, and I've done a QQ plot. So if you remember QQ plots, you can take your observed data and you can look at it against the theoretical distribution. So here I'm doing against the theoretical distribution, which is an exponential with a rate of 2. And if your observations are from that distribution, the points should lie on a straight line. And in this case, you can see they do. The only slight deviation is in the extreme values, but that's pretty good. And that's how R does it. It often does. It has all these inverse CDFs built in for a lot of common distributions. Okay, so that's it. That's your first indication of how to simulate data. There's lots and lots of different methods. We'll discuss some of them later in this course. And next time we will do the motivated example. Thank you very much. See you next time.